Our first presentation this morning in bridge wearing surfaces is going to be Ray Breer from e-Chem, and he's going to talk to you today about epoxy resin polymers.
Good morning, everyone. My presentation today is on using epoxy polymer concrete for grade correction. This was specifically for a project that we did in New Mexico in the Jemez Canyon. There was a new bridge construction, and during the installation process, the shoring over the river settled, and they had some extreme elevation issues once they completed that pour. This is the structure here that just prior to pouring it, when we came in there, they actually did a heat map. We quantified the material, took down the high spots to reduce the material load on the structure. Reasons for grade correction are numerous, so it can be a field elevation bust, construction deviation, plan elevation bust, roadway correction, or a construction event like what happened on this project. When we look at using Epc Overlay on the grade correction, there's certainly specific project considerations, structure suitability, make sure it'll take the extra material load that we're putting on there, thicknesses required, load requirements, ADT issues, and environmental concerns. We want to make sure that we have proper temperature and weather considerations there, and time constraints at hand. So what is epoxy polymer concrete? Epoxy polymer concrete is very similar in use to Portland cement or traditional Portland cement concretes. We take aggregate, we take sand, and we use epoxy polymers as a binder. Kind of the secret to the sauce here, we need to keep the resin loading very low for our EPC concrete. We target 10.5% to 12% by weight. So it kind of works out in this matrix: 10% epoxy, 30% coarse aggregates, and 60% sand. Very similar to a Portland cement mixture. So why EPC Overlay? So we developed EPC with a very specific target. We wanted to make sure it's going to meet the future environmental concerns. We have zero VOCs, no HAPs, very low odor, rapid curing, we're moisture insensitive. It's a rapid return to traffic. So in 3 hours at 73 degrees, we're traffic ready. So if there is, time constraints and there are concerns for short traffic closures, this is a very well-suited product. Different applications, obviously the whole-scale bridge deck overlay application that we're going to discuss, bridge joint nosings, replacements, abutment repairs, pothole and deck repairs, grade correction, rut infilling. It's really a multiple use product. So during the installation process, we're going to quantify the material needs like we discussed, evaluate the environmental conditions, deck preparation, forming, primer or pre-treatment, mixing, placing, finishing, cleanup, and then making sure we have the proper cure time. This is the heat map we developed for this project. As when they were pouring it, as they got about a third of the way across the deck, that's when the shoring settled down. At the end of it, we had about a 5.5 inch elevation deviation from highs to low on this deck. It was pretty extreme. There were multiple concerns about this project and the viability of rescuing this deck. So we were able to come in, help the DOT come up with a process, and came together with a contractor to get this done. So it was about a 60-day delay by the time we started, evaluated it, and got it to the point where we were able to correct it. So we figured out how much material we needed. We got all the material on site. Surface preparation, after we milled the high spots down, came in, shot blasted. Shot blasting is a process where we're abrading the surface, creating a surface profile that makes it a suitable bonding surface for the EPC overlay. Getting the deck ready to place for forms, we need to figure out how are we going to screed and place this material. There's multiple ways and processes to do this. On this project, the contractor chose to use a vibrating pan screed with screed rails. In this process, what they do is they'll place a screed rail for their paver. They'll set the elevation, make sure it's anchored. We'll do a dry run and check elevation throughout before we even place the material. We want to make sure it's going to be a one and done installation here. If it's a bridge deck paver like a Bidwell, same process. We'll set screed rails, we'll get the elevation correct, do a dry run, and proceed with that. Self-propelled pavers out there, it's kind of the newest technology. They'll set a guide wire on both sides, and that's the elevation control for the paving equipment. And it's critical that whatever process is used, that we're confident in that elevation. This is the project we were looking at earlier. This is the first pour on it'd be the south side of the bridge. They actually use the edge forming from the original pour for their screed on the south side, and then they set their elevation on the north side. Here's a representation of a bidwell paver where they set the screed rails, hung them off the bridge rail on one side, and then set a pipe on the other. And then the right picture is the Hemis project where they were doing the dry run with their screed paver. A couple more pictures. The Hemis was actually a really nice location. But it was cold in the mornings because we had that river high elevation, about 8,500 feet at this point in the valley. This picture was a project we did in Oregon. It was a fire service bridge that they tried to put a couple of different overlay systems on it. They weren't able to complete it just because of the location. It was a very remote location, and we were able to get the EPC in there and get that project done. We got the truss screed set on the deck. We're talking about doing the dry run to make sure that we have good clearances. We don't want to get too tight. We need a minimum of a 3/4 inch clearance. That's the reason we do that dry run. Primers installation, the reason we use a primer or pre-treatment is to address any surface cracking. We want to make sure we address surface cracks, we fill them. If that way, it's kind of a belt and suspenders application, so we can fill and seal off any subsurface cracks there. The primer goes on very thin application, anywhere from 70 feet to 120 square feet a gallon, depending on the surface texture, porosity of the deck. It's a flood coat, and then they'll come back and they'll push the excess forward with brooms, squeegees, rollers. We want it really as thin as possible. We don't want to have an excess of material in that bond area. A couple more pictures of putting down the primer. Some contractors choose to spray it. So the EPCA comes in a couple different packaging options. We have small bag kits all the way up to bulk packaging like we did up here in Hemis. So the bulk packaging is going to be more for the volumetric equipment, automated batching equipment. So this is a semi-bulk where we're actually pumping the resin through continuous pumping systems, and then we just break bags into mixers. This is the volumetric truck that we used up in Hemis. It's a smaller truck, about 6.5 yards. A few pictures of the placing. The placement's very similar to Portland concrete placement. It's a higher slump product. It actually places and smooths very well. We use a vibrating truss screed. We want to make sure we get any of the air out of the material, and there's a resin that will float up to the surface, and we'll put a traction aggregate into that surface. This is a hand mix application where all the liquids come pre-measured, pre-packaged, and then we bust bags of aggregate into a mixer. This was that project up in Oregon. This we're doing 1.6 cubic foot batches. They just use wheelbarrows or muck carts to take it down the bridge. This is a volumetric installation. This is in North Carolina. This provider actually has an office and facilities here in Pennsylvania, so this equipment is available up in the Northeast. Finishing, so when we finish the Epc Overlay, it's going to be very similar to any Portland concrete finishing process on a bridge deck. We can use truss screeds, we can use bidwell pavers, slip form pavers, so it's there's a lot of different equipment options for contractors, so we're not limiting the construction process to one group of professionals. This is the finishing with the truss screed. Very quick, we just finished a project in Idaho as a FHWA stick grant. Used the same process up there. It was a demonstration project to show that even city and county crews can do smaller installations with crews and equipment they have on hand. So and this is finishing it using a bridge spec paver bidwell. This was North Carolina. 4 bridges we completed in one weekend. You see with the bidwell, it's very similar to any other bridge topping process with this system. And this is the automated paver where they set the string line for their elevation. You dump the material in front of it, it places, finishes, and gives you correct grade as it proceeds down the deck. And then for the edges, so the hedges are completed by handwork. It's just smaller batching, come in and tie in the areas that the pavers miss. And then for your finish course, we can do tining, saw cutting, grooving, or just leave a high friction surface course or aggregate wearing surface for your final placement. And then the aggregate course is just a hand broadcast to address any loose resin that might be there. We don't want to provide a dangerous driving surface. Resins can be very slippery when they get wet. So as I stated up here, so we're in an FHWA stick grant in Pennsylvania. We completed the viability study using Pennsylvania. Up in Pennsylvania, they're finishing the final construction specification now. New York State, we're approved in New York State on the APL, QPL for overlays, repair products, and same with North Carolina for the Northeast areas. So anyways, any questions? Yes, sir.
A question. When you were...
The truss screed?
Yeah,
yep.
the truss screed.
Mm-hmm.
You mentioned...
It's kind of a timing thing. It's usually within 5 to 10 minutes.
You're back there dusting and then...
Yes, that's correct, yeah. So we want to get a little bit of that resin to float, and then we'll just tie in the edges. As soon as that's done, we're ready to put the aggregate on there. So it's just a few minutes later we're putting the aggregate on there.
Screens and you're sort of with the epoxy.
We use a delimonene. It's an orange-based, solvent-based cleaner, or some contractors just use water in a power washer. And then they'll collect the water. They let the epoxy set, and then it's an inert trash material at that point. They just filter the water out. And so it's from an environmental perspective or worker safety standpoint, we're not using, harsh chemicals or products to clean up or to maintain the equipment after the fact. So, all right, thank you. Yes, sir. So so epoxies are exothermic, so it's all going to be temperature driven. So at 73 degrees, we'll hit 3,500 psi in about 3 hours. So it's kind of, when you're placing it, you're thinking, man, is this stuff going to get there in 3 hours? Because at about 2 hours, it just starts to take off. As soon as it starts to build that heat within the matrix of the system, and then literally goes from a gel state to traffic ready in 60 minutes once it starts to react. And vice versa, at 60 degrees, we're going to probably go to 4.5 hours. At 80 degrees, we're an hour and a half. So, okay. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.